Pressure is well known to be a fundamental part of meteorology. Many years ago, scientists saw a strong relationship between the distribution of pressure and the weather. This led to one of the simplest instruments called the barometer, which many households use for ornamental purposes. These were developed well before the 19th century and are still used today. Over the years, more complex instrumentation has been developed to measure atmospheric pressure to the degree of accuracy required for aviation. The forces generated by horizontal pressure differences give rise to horizontal air movement and therefore winds. The vertical variation of pressure gives us the ability to measure the height of an aircraft above a surface. The instrument that measures this variation is the altimeter. As pressure is reduced with height through the atmosphere, the altimeter will read a higher value. As you can see, pressure is fundamental to meteorology and aviation. This lesson aims to give you an understanding of pressure in our atmosphere and its significance to us as aviators. What is atmospheric pressure? The air in the atmosphere is made up of particles, and as a result, these will be subject to gravity that will tend to pull the particles downwards. Therefore, any area on the Earth's surface will have to support the weight of the column of air directly above it. This weight is otherwise known as atmospheric pressure. The less air in the column, the less the pressure will be at the surface. The higher and higher we go in the atmosphere, the total amount of air overlying us decreases. Therefore, the less the weight of air above, the less the atmospheric pressure. So, pressure decreases with altitude. We will now look at how pressure is measured and represented in meteorology. As we mentioned earlier, traditionally pressure was measured using an instrument called a barometer. There are two types, an aneroid barometer and a mercury barometer. A mercury barometer consists of an inverted glass tube of mercury with its open end inside a reservoir at the bottom. When high atmospheric pressure is experienced, the force or weight of the atmosphere will depress the mercury in the open reservoir and force more of the mercury up into the tube. This displacement is traditionally measured in inches. The higher the column of mercury, the higher the atmospheric pressure. The other type of barometer is non-liquid and is therefore called an aneroid barometer. These can be less accurate than mercury barometers, but are more sensitive to small changes in air pressure. An aneroid barometer measures the effect of air pressure on a metal chamber from which part of the air has been removed. Changes in air pressure make the chamber expand or contract, moving a needle on a dial. The dial may be scaled in millibars, inches or millimeters. These light and portable barometers are widely used in homes, offices and schools, and importantly for us, in aircraft. Often, a special type of aneroid barometer, called a barograph, is used to record changes in atmospheric pressure over time. A barograph includes a pen that records the air pressure on a paper chart, mounted on a rotating drum. Going back to the mercury barometer, once calibrated, the average sea level pressure will displace the mercury from the level in the reservoir by 29.92 inches. The United States usually use inches for measuring pressure. However, elsewhere it is more common to use the millibar or hectopascal to measure atmospheric pressure. This uses a different scale, but for comparison, 1013.2 hectopascals is equivalent to 29.92 inches of mercury. In recent years, the adoption of the metric hectopascal has been replacing the millibar. However, do not worry because the hectopascal and the millibar use the same scale. 1013.2 millibars is also 1013.2 hectopascals. In summary then, 29.92 inches of mercury is the same as 1013.2 millibars and 1013.2 hectopascals. Remember from the atmosphere lesson that this is the atmospheric pressure at mean sea level according to ISA. Next, we will look at horizontal variations in pressure. Now we need to analyse how we might show pressure variations across a region. This is important because then we will be able to identify if one area of a surface is experiencing higher or lower pressure than another area. In order to remove the pressure height anomaly, i.e. the vertical pressure variation, we reference our observations to a common horizontal level, usually mean sea level. If we look at the diagram, we can see various stations reporting their particular pressure values. If we now draw a line connecting all the areas with the same pressure, we end up with a pattern of lines over the surface. These lines are called isobars, and they join places of equal pressure. Using these pressure values, we can identify areas of low and high atmospheric pressure. Lower value isobars indicate a low pressure. A concentric low value enclosed isobar shows the lowest pressure and reveals the center point. These systems can range from tens of nautical miles wide to hundreds and even 1,000 miles wide. Note though that the spacing between the isobars in the low can be smaller than those found around high pressures. This means that the pressure gradient, or the change in pressure with distance, can be greater within a low pressure system than in a high pressure system. By watching the isobars change shape over time, we can see how these systems behave. If they were to intensify or deepen, we would see new concentric lower value isobars appearing within the central part of the depression. If the isobars move outwards from the centre, then the depression is growing outwards and covering a wider area. If we see low pressure isobars protruding outwards from the low pressure into an area between two highs, we call this an isobaric trough. As you can see, isobars are a very useful way of visualizing pressure patterns and hence the weather. Next, we will take a look at high pressures and how they are depicted. Basically, a high-value isobar indicates a higher pressure. An enclosed high-value isobar shows the highest pressure within an area and reveals its center. As mentioned previously, note that the isobar spacing in high pressures tends to be further apart than the low pressure systems. We will return to this point again shortly. By watching the isobars, we can see over time how high pressures can change. New concentric higher value isobars developing in the center of the high indicate the high pressure is intensifying. If the isobars around the high were moving outwards, we could see the high pressure is growing. If we see the isobars protruding outwards from the high pressure into an area between two lows, we call this a ridge. It signifies an extension of the high pressure into another area, spreading its influence. Looking at the chart, it is possible to identify areas which are not high or low pressures. These areas are generally found between highs and lows and are called cols. They are synonymous with calm conditions. High pressures, low pressures and cols are dealt with in considerable detail later on.